Okay, I think we're ready to go. It's always awesome when you're almost standing room only, but there's enough seats for everybody. So thank you all for coming out today. So happy Engineers Week, first of all. Happy E-Week. For those who don't know me or if you've only seen me in a mask, I'm Rich Corsi. I'm the Dean of the College of Engineering here at UC Davis. And we're thrilled to have you here in person and online. I think we have a pretty large online contingent for this as well to celebrate E-Week with the launch of or relaunch of our Dean's Distinguished Speaker Series. Today's distinguished speaker is Professor Linsey Marr, the Charles P. Lunsford Professor of Civil and Environmental Engineering at Virginia Tech, and she'll present a talk entitled An Engineering Perspective on the Secret Lives of Airborne Viruses. On a personal note, I first met Linsey when I was on sabbatical for a semester at UC Berkeley in the spring of 2001, and she was a Ph.D. student in environmental engineering working on outdoor air pollution research at that time. And here we are 22 years later, and I have the honor to introduce Linsey as a Dean's Distinguished Speaker in our College of Engineering. Linsey received her Bachelor of Science in Engineering Science at Harvard University and a Ph.D. in Environmental Engineering at UC Berkeley in 2002. She completed a postdoc in Earth, Atmospheric, and Planetary Science at MIT. She joined the faculty of Virginia Tech University in Civil and Environmental Engineering in 2003. And amongst many different contributions that Linsey has made, two really big areas are in the areas of airborne engineered nanomaterials and virus transmission of bioaerosols. And it's in that latter area where Linsey has taken her expertise in aerosol science, airborne viruses, building science, and inhalation dose reduction by different mask materials and made truly extraordinary contributions to society around the world during the current pandemic. Since March of 2020, Dr. Marr has given hundreds of interviews and been quoted over 4,000 times in 79 different countries. She's used her expertise to help educate the World Health Organization, the White House Office of Science and Technology Policy, and several members of Congress. And Lord knows there are some there that need some educating. So consider the following passage from a lengthy article in a June 2020 New York Times profile of Dr. Marr entitled, "The Scientist, the Air, and the Virus." Quote, "Most of us had never heard of aerosol science before the pandemic. Then Virginia Tech's Linsey Marr showed up and became our personal tour guide to the invisible world of airborne particles." Again, that's a feature in the New York Times just a few months after the start of the pandemic. Linsey has a long list of well-deserved awards and recognition, and I can't go through all of them, so I'm just going to mention a few from the last 24 months. In 2021, she became a fellow of the American Association for Aerosol Research, AAAR, and also received the Suzanne Herring Award that year, which is a big award in that association. She is Virginia Tech Ut Prosim Scholar Award recipient, which is the highest honor for a faculty member at Virginia Tech University. In 2021, she was also inducted into UC Berkeley's Civil and Environmental Engineering Academy of Distinguished Alumni. In 2022, she became a fellow of the American Geophysical Union, also received one of their large awards that year, was the Walter J. Weber Jr. Association of Environmental Engineering and Science Professors Frontier and Research Award recipient in 2022. She received the Outstanding Faculty Award from the State Council of Higher Education for Virginia. That's the Commonwealth's highest honor for faculty at Virginia's public and private colleges and universities, all universities in the state of Virginia, and it recognizes superior accomplishments in teaching, research, knowledge integration, and public service. And in 2023, just a few weeks ago, we learned that Linsey has been elected to the National Academy of Engineering. There are a lot of other research awards, numerous teaching awards, innovation awards. I won't summarize anymore other than to say, wow, it's truly an extraordinary record. On a personal note, as I said, Linsey and I have known each other for many years, and I really appreciate how centered she is, how much she has meant to her field, how much she's never let her success affect who she is at the core. And that's a deeply dedicated scholar who uses her expertise with a deep commitment to doing good for others. That's a very long introduction, but it's wholly deserved. And with that, please join me in welcoming Dr. Linsey Marr as our Dean's Distinguished Speaker in the College of Engineering.
thank you to Dean Corsi for the very kind introduction and also for inviting me. This is a bit of a homecoming for me because I grew up in Sacramento, and when I was a kid, in high school especially, I visited Davis many times. It was the very cool college town 20 minutes down the road. I want to start out by acknowledging my many collaborators, faculty, postdocs, and graduate students, and undergraduates along the way. Currently, I lead a large multidisciplinary effort called Mitigate Flu to better understand transmission of flu. This started before the pandemic, and we have been graciously funded by Flu Lab and Welcome Leap in recent years, along with other sources along the way. So I'm going to start somewhere that's very traditional for this field, which is the influence of air pollution on our health. There's a large ongoing study called Global Burden of Disease, and they look at all the reasons why people get sick and die around the world. And it turns out that air pollution is responsible for 7 million premature deaths per year. And this figure, the bar across the top, shows the colors each show the kind of different actual causes of death. And for air pollution, the biggest section is that blue in the middle, which is due to cardiovascular disease. And if you look at these other environmental and occupational risks, air pollution ranks #1 far and away. The next biggest is heat or cold. And then we hear a lot about water quality. Well, water, sanitation, and hygiene accounts for about 2 million. Then there's occupational hazards. The eagle-eyed among you will notice that on heat or cold, there's some negative deaths. It'd be great to get into that category. I'm guessing that that's because in places that are really hot, that are cooler now, or places that were really cold or warmer now, there's fewer deaths there. Anyway, air pollution is a huge cause of morbidity and mortality around the world. Traditionally, when we think about air pollution, we think about compounds such as ozone, a gas that forms in the atmosphere and causes respiratory irritation, or particulate matter that's responsible for most of those deaths that you saw on the previous slide, or carbon dioxide, of course, a major greenhouse gas. Now, I started thinking about other things in the atmosphere that behave like particulate matter, but are not in those traditional categories of pollutants. And one of the things that we got into when I started at Virginia Tech was engineered nanomaterials. They were emerging, being more widely used in industry and in products, and we were concerned about potential for exposure to them, kind of what happened to them in the environment. And so we did many years of research on those, including looking at spray products. And our experience with that actually helped inform a lot of our experiments and kind of knowledge that we developed surrounding airborne pathogens. Because a virus, to me, was really just an ideal engineered nanoparticle, one that's really cool because it self-replicates. But really, once it gets into the atmosphere, it's just behaving like any other particle. And so what I did was to really take this engineering approach that we had used, the whole field had applied to air pollutants, and to then apply it to airborne pathogens. So in traditional air pollution kind of engineering, and we think about a source of emissions. It could be a power plant that burns fossil fuels, or vehicles, or maybe some kind of factory. It releases those emissions into the atmosphere, and then they get transported. They can undergo transformations in the atmosphere, either chemical reactions, or if they're particles, they can go under physical transformations where they maybe aggregate with other particles, or they become coated by things that condense on them. Do you have any, I'm getting a lot of noise from I don't know if that's brushing or when I'm moving around. Do you have any suggestions here? Or? Okay, sorry about that. So those undergo further transport through the atmosphere, and then eventually people can become exposed to them. That can lead to health effects. Well, we can apply this same model to airborne pathogens. So somebody coughs, sneezes, talks, breathes, and they release respiratory particles into the atmosphere. Those might contain pathogens, a virus, for example, if they are infected. And that virus can undergo transformations in the atmosphere also. It can be degraded by UV light, It can be affected by salt and other components that are in the particle that carries it. Maybe pH affects it too. And then again, it's transported and somebody can be exposed to it and become infected. And so everything, the world that started changing in 2020, and this is an article that came out in the New York Times in January. And they were asking the question of how bad will the coronavirus outbreak get? And here are 6 key factors. One of those factors was how far viruses travel. And they said, based on existing knowledge at the time, they didn't talk to the few people of us who actually knew what was going on, but they talked to the kind of the textbooks, or what people said from the textbooks, and said, well, coronaviruses can travel only about 6 feet from the infected person. It's unknown how long they live on surfaces. Some other viruses, like measles, can travel up to 100 feet and stay alive on surfaces for hours. So I saw this, and then I tweeted it out. I'm not sure I believe that coronavirus droplets fall to the ground within a few feet, while measles, chickenpox, and tuberculosis can travel about 100 feet. But why do people think this? It boggled my mind. We had been studying influenza virus for 10 years at this point. We had found it in very small particles, the type that can travel well across this room. And it appeared to me that the same thing was happening with the coronavirus. And so now I want to get into the meat of the talk, which is kind of the secret lives of airborne viruses. So we're going to look at a couple of main questions. The first is, how do viruses get into the air? Because that'll help us then understand where do they go. And I'm going to cover 3 different fates of them. One is that they can end up on the floor. The second is that they could go out the window. And the third is that they could be trapped on a filter. And around the room, you'll see there's these big box fan type filter things. And so those are our filters that are trapping any viruses, hopefully, that might be in the air. And so when I was making this, I was thinking, oh, the floor, they go out the window, they go out the door. And then I, of course, thought of the song On Top of Spaghetti, All Covered with Cheese. I lost my poor meatball when somebody sneezed. It rolled off the table, so it falls onto the floor. And then my poor meatball rolled out of the door. And so I guess the viruses are like these mini meatballs, and we're going to follow them around. And so the first question now is, how do viruses get into the air? I have a video to show you. It's about 1.5 minutes, and there's some music to it. And you'll have to, it's in slow motion, so we'll just watch this. Oh, and this came out in 2009, well before the pandemic. From Australia, the public health messaging there. It's amazing what you can do with a high-speed camera. So in that video, that was gross, right? We saw things coming out of people's noses and mouths, and people thought, I guess, at the beginning of the pandemic, well, and this is kind of conventional thinking about how respiratory illnesses were transmitted, was that I cough in your face, and those large visible droplets fly through the air, and they land on your eyes, your nostrils, somehow they get in there, or they land on your lips, and that's how you become sick. And so people were well aware that an infected person has symptoms. They can release these large droplets when they cough. I think what they didn't realize is that for every large droplet that you saw in that video, there were hundreds of tiny droplets, aerosol particles that we can't see. So they're too small to see, but they are there. And this is a cartoon that my son made out of this, depicting this. And this just was not, there was not a lot of awareness about this, even though in 1946, there was a paper published where they had subjects, maybe it was the authors themselves, but they painted, I think the inside of their mouths and lips with some kind of like red dye or a colored dye, and then had them cough or talk, and then they put these slides in front of them and caught everything that they could on there. And then they counted and measured under a microscope and found these size distributions of what was being released. So that, again, this is back in 1946. There's a couple things to notice here. First of all, the x-axis is shown in the log scale. So we've got 1, 10, 100, and 1,000 micrometers. And the y-axis shows you the number for coughing. So this is from one cough, and that's shown in the red. And then the pink shows the number that is emitted for talking when you count from 1 to 100. The scale on the left side is about 20 times higher than on the right side. So if I cough, I'm going to release about 20 times more than when I talk. Although maybe if I talk, I'm talking here for, what, half an hour? So that'd be saying 1 to 100, maybe 30 times. So that's like 15 coughs or so that I'm. And notice that the size is distribution, the shape of that is similar. So when someone's talking, they are releasing particles. It's not as many as when they're coughing, but if they talk for a while, they're going to release as much as somebody released in a cough. And the majority of these clearly are in this smaller size range, so smaller than about 30 micrometers. There's a few out here in these larger visible droplets, and this is where people had presumed all the action was, but notice they were unaware of all this going on, or just hadn't looked at this paper from 1946. And actually, since then, using more modern measurement techniques, people have shown, including Chris Kappa and his group here, have shown that there's actually even more particles in this small, kind of around micron size range particles, like hundreds more up here. And so there's a lot of those tiny red aerosol particles that come out of our mouths, even when we're just talking. So viruses are very small. I want to kind of get a better feel for these different sizes we're talking about. Your hair is about 50 to 70 nanometers in diameter. And then we talk about coarse particulate matter, or PM10, so that's 10 micrometers. We often talk about PM2.5, which is 2.5 microns in diameter. That's what's responsible for a lot of those premature deaths I showed earlier. And then a virus is, the coronavirus is about 0.1 microns in size. And so this pink figure shows a particle that's 2.5 microns. The virus itself is tiny, 0.1 microns. That's shown to scale. So the virus itself is very small, as we all heard. But viruses are carried in larger respiratory particles, these droplets and what I called aerosol particles. The airborne virus is not naked. It is not floating around in the air like this. It can't be released that way. In fact, it's released in droplets of respiratory fluid that can range over in size from, I showed you on that previous graph, from maybe 0.2 to 100 microns, or even larger for those big goopy ones that we saw in the video. This figure shows a 0.5 micron particle with the virus shown to scale. And it's really the size of this carrier particle that defines the transport of the virus. It's not the size of the virus itself. And this determines how long the particle stays aloft, how quickly it falls to surfaces, how far it can travel, where it deposits in your respiratory system if you inhale it, how well it's removed by masks and filters. And the physics is the same for all viruses. It's not like one virus can travel farther than another. Really, they're carried in these respiratory droplets. So remember, I showed you that New York Times article that said, oh, coronaviruses can't travel as far as measles or tuberculosis. Maybe it appears that some are more transmissible than others, but that's not because they're in they're different sizes or they travel farther or less far. It has to do with how much somebody releases if they're infected, how well that virus or bacterium survives in these droplets, and then how much you have to breathe in to become infected. And so these respiratory droplets or particles are not just water. They contain lots of stuff. There are non-volatile components, so even if you remove all the water, 1 to 9% of the initial mass of that droplet or particle does not evaporate. And so this electron micrograph over here shows some of these evaporated particles. This is done by Papinini et al. And you can see the scale bars here, so 1 micron. And these are mostly, looks like salt crystals to me. And then I'm going to show you the virus for scale. So again, it is not the naked virus. It's floating, it's around in all this other stuff. And now, we have been, this is some new data that I've never shown before. We have not published this yet, but we collected exhaled breath samples. We had people talking, 3 different people, subjects A, B, and C, and collected those particles onto a TEM grid. And then some collaborators at Pacific Northwest National Laboratory have analyzed these using computer-controlled TEM with electron dispersive X-ray spectrometry, EDS, to look at the elemental composition of the particles. And then they categorize them into 5 different categories. And the particles are heterogeneous. They are different from one another. And we've done this by size too, but I'm just showing you here kind of the overall categorization. So you can see that half or more of the particles from these different subjects are green. They're organic. And so that's mainly the protein content, or they're dominated by protein and other organic compounds. And then the rest of it's mostly these sodium-rich salt particles, so sodium chloride. That's no surprise. It's in our salt. It's in our saliva. And then we have smaller amounts of potassium-rich salt and phosphorus, and then some mixed particles. Now, that's what's coming out. And what happens when these viruses are released into the air? Well, first of all, they evaporate and shrink, depending on the ambient humidity. And in this room, it is, I brought my carbon dioxide sensor, which shows 875 ppm, which is not bad for this many people in a room. The humidity is 32%. And so this graph shows on the y-axis, it shows the ratio of the final to initial diameter. So 0.5 would mean that it shrinks to half its initial size as a function of relative humidity. And if we start with a 10 micron particle that somebody releases. And now this is cartoony in that these are not to scale. I have a virus in there, and I have some salt and protein in there. It comes out of our respiratory tract, which is very humid. It hits the ambient air, which is dry, and some of the water is going to evaporate as that equilibrates. And we can predict this according to the Kohler equation. And at 20% humidity, or in this room we're around 32%, right? So we'd be around here, but you can see it shrinks to about 40% of its initial size. So now it's 4 microns in diameter. We've lost the water, but the non-volatile components have not been lost. They're still there. This has become more concentrated, or perhaps it's probably even desiccated at that conditions. And now these viruses, or kind of our respiratory particles in general, can accumulate in air over time. If I were smoking a cigarette here in this room and the ventilation were poor, the room were closed up, eventually you would know the smoke would kind of fill the room. And so likewise, these particles can accumulate in the air and end up filling the room. So it's even someone who's far away from the person, the source, someone who's far away can be exposed. And the particles now have different fates. We're going to follow 3 different particles that have been released. So first, we'll look at one and consider it settling to the ground. We'll look at another and see how it can be removed through ventilation. And then we'll look at a third that gets trapped on a filter. So the first fate is settling, where things end up on the ground. Notice that they are, in this depiction, they're on the ground everywhere. They're not just on the ground below the person we're concerned about. And so this is very mathematically predictable, how fast particles settle to the ground. Every environmental engineer learns this equation for the settling velocity. You can derive it by balancing gravitational forces and drag and buoyancy. And the settling velocity is a function of the diameter of the particle squared. So larger particles settle faster, smaller particles settle more slowly. And here I show the time for a particle to settle from a height of 1.5 meters, which is almost 5 feet high, so like, just above my nose or so. And you can see these larger particles, they settle quickly within a minute or two. But if we look at a 5-micron particle, it actually takes over half an hour to settle from a height of 1.5 microns. And somehow in the medical literature, they had, things had gotten messed up along the way, and we delved into this with a historian, but they had described particles of this size, 5 microns and larger, as behaving like droplets that immediately fall to the ground. But you can see here that, in fact, it takes half an hour for this to fall to the ground. And in the meantime, while that particle is falling to the ground, there are there are air currents in the room that can carry it far from where it was initially released. Even if you're in a room where the air feels very still, the air is still moving due to temperature gradients and pressure gradients and infiltration through cracks in the walls and things. And so this graph shows how they can travel more than 6 feet. This actually shows the trajectory of a particle. I have different size particles. We've got a 5-micron particle here released from a height of 1.5 meters. And if we have the case of a low indoor air velocity, air moving at 5 centimeters per second, this particle would travel over 100 meters, so over 300 feet, which is way more than the 6 feet that we had all been warned about. And even a 10-micron particle is going to travel 25 meters, and you can see the 20 and 30-micron particles would travel a few meters at least, certainly more than 6 feet. And this does not mean, this is kind of a depiction. They may not be going in a straight line. They may be kind of moving around horizontally through this path, so it's not like it's going from here all the way to the other room on the opposite side, but it could take this meandering path that ends up where it travels a horizontal distance of over 100 meters. And then at a high indoor air velocity of 20 centimeters per second, that stretches out the x-axis here. So now what was 100 meters is now 400 meters, and everything goes a little bit farther. So things can end up on the floor. We had also worked on the idea that of particles in the room, maybe half of them are actually resuspended from people walking around. So we published a paper on that a while ago too, because I was really interested in the idea. If you imagine you're walking along a dusty street kicking up dust, there's going to be more kind of at your feet, more closer to the ground, and less that reaches higher heights. And that was inspired because my spouse is a foot taller than me, and he never seems to get sick, whereas the kids and I always get sick. And so I was wondering if these viruses sitting on the floor were being resuspended. There was a concentration gradient where the shorter people got exposed to more. And our modeling showed that, in fact, yes, I think the kids were exposed to maybe 20% more. I don't think it made a big enough difference, but it was still an interesting exercise. The second thing that can happen with these particles that are released into the air is that they can be removed from the air through ventilation. So ventilation means we are bringing in outdoor air or somehow cleaned air and pushing out the older air. And we can actually predict virus concentrations in air in a space. In this, let's say here's our room. We have someone who releases respiratory particles into the room. And we consider their removal by ventilation or settling. So I've talked about settling, and we're talking about ventilation now. And then we were also considering removal by inactivation, where the virus dies off or decays over time. And because this is an engineering lecture, I have a differential equation, but this is the only one. And so we can actually use assume a well-mixed model, and then calculate the concentration of infectious virus C sub d in particles of a certain diameter d as a function of time. So there's that all of these losses processes we can model as first order decay, and this term shows removal by gravitational settling, where we have that settling velocity v sub t. This lambda refers to the air exchange rate or air change rate. You may have heard about air changes per hour. So that's removal by ventilation. And then things can be removed. The virus is not physically removed, but it is inactivated, and it can be kind of biologically removed through inactivation. And so in this next figure, these show the removal efficiency of different processes under two different conditions. So don't worry about the details, but if you just look at these two figures, kind of big picture, what is the big difference you see? The big difference is this ventilation, the amount that's removed by ventilation, or the removal efficiency. And the difference in these two scenarios is that on the left-hand side, I have an air change rate of 1 air change per hour. So every 1 hour, approximately, the air is replaced in this room. On the right-hand side, I have an air exchange rate of 10 air changes per hour. So that's happening 10 times per hour, like every 6 minutes. And this is, in hospitals, you get 6 to 12 air changes per hour. In schools, you might be or in homes, you might be somewhere around here. And so you can see that, again, with higher air change rates, you get a much higher removal by ventilation. So it shows you the power of ventilation. Settling is shown as pretty significant here because we are considering the entire size range of particles that are removed. And if there is more virus in those larger droplets, they settle quickly and that removes it. We're not worried about that for airborne transmission. It's kind of everything else that we're concerned about. And now I want to talk about the third possible fate that I'll cover today of the virus in the air, and that is filtration. So you can buy, you've probably seen in different places, doctor's offices, classrooms maybe you have one in your home, a portable HEPA air cleaner. To get one that will fit your bedroom or kind of a living space, you'd have to spend $200 or $300. And so that's a lot of money for a lot of people. And so a lower cost do-it-yourself version of this was proposed. And it was actually Dean Corsi who proposed this idea in a tweet, I believe. Is that where it first came out? He kind of floated this idea. And then Jim Rosenthal went ahead and actually built a prototype of this. And it's really elegant because it takes very easy to acquire materials, and this was back in the days of the pandemic when you couldn't find anything, toilet paper or anything at the grocery store, and you just needed a box fan, which a lot of people already have, that's item A, and then 4 HVAC or furnace filters, which I'll talk about in more detail in a minute, and then kind of a bottom, you would put a shroud around there to make it more efficient and help with the noise. The shroud is just the kind of a cardboard cutout. And you can see that on these here. So we have 2 Corsi Rosenthal boxes here, and they are happily spinning away. Now I want to talk a little bit more about this filter. So this is useful information when you're shopping for filters for your home HVAC system. Filters are rated by their quality according to the MERV scale, minimum efficiency reporting value. Now I know Home Depot and Lowe's have their own, and 3M, I think, each have their own different rating scale, but I think they also will have the MERV rating. Higher numbers are better, and for the Corsi Rosenthal box, they recommended MERV 13. And this figure shows the collection of the filtration efficiency as a function of particle size, and again, this is a log scale. Now, all these curves have this U shape, where the minimum occurs somewhere between 0.1 and 0.3 microns in size. And that's surprising to some people because I think that we commonly think, oh, filtration and anything, if it removes 50% of particles at 0.3 microns, then it's going to remove even less of the smaller particles. But in fact, as you go to smaller particles, you remove more of them. And I'll talk about that more in the next slide. So the MERV 13 filters are not as good as a HEPA filter. A HEPA filter maintains efficiency close to 1. It's like 99.97% at 0.3 microns, so it's a lot better. MERV 13 is down here, and you think, oh, well, that's not so great. But I would say that the particles that we're probably most concerned about more concerned about for transmission are over in this shaded rectangle area, maybe 0.7 to 1 microns, because that's where a lot of our emissions come out, and those particles can stay floating around for a while, and they can deposit in our respiratory tract. And then I highlighted here that MERV 13 line in this region, and you can see the efficiency is around 80%. You may say, well, that's not great. It's not all that great compared to a HEPA filter. The nice thing about these, though, is that they move a lot of air. So the air passes through there, I remove 80% of the particles. Then the air passes through there again, and I remove another 80% of what remained. And so, because they're moving a lot of air through those filters, we can actually achieve a really excellent performance. And that I'll get to in a minute. So again, I want to talk a little bit more about how filtration is not sieving. And we need to shrink ourselves down to the size of a particle. And imagine we're trying to fly through this filter where we see all these fibers. And so now we're kind of looking at an individual fiber in the filter, and we are the particle. The air has to flow around the fiber, And as it curves around there, maybe we have a little too much momentum and we crash into the fiber. That's one way of removing the particle. Or maybe that streamline passes close to the fiber as it's going around, and the particle brushes up against the fiber and gets stuck. And then for these really small particles, in addition to being carried by the streamlines, they also undergo random motion, which is like diffusion, and they can wander out of the path and end up crashing into the fiber, and that's how those very tiny particles are very efficiently removed. And in fact, there's, if you're interested in seeing this further, I talked about how you shrink yourself down to the size of the particle and weave through this forest of fibers. The New York Times ran this nice visualization about masks, and they showed a magnified view of the fibers of a mask. And as you step through this animation, you would be flying through the fibers. And I think this is great because I always wanted a visualization like this to show my classes, and then they created it. I helped consult on this for them. And as they explain here, the smallest particles are bounced around by air molecules in a random zigzag pattern, increasing their chances of getting captured. If you haven't seen this, I recommend it. You can look up Masswork, really will show you how. And there's even a cool smartphone version. I don't know why they did this, but there's like a VR component where you can hold it up and you can see the particles flying through the background. And so now we get to the take-home of this about the Corsi Rosenthal box. It performs better than that $200 or $300 HEPA air cleaner that I have at home and I like. So this shows the CADR, clean air delivery rate. These colored columns are the clean air delivery rate. And that's the number where you want a higher number. Higher is better. That's more clean air the more air that's being cleaned by these filtration units. And they show that, so this was an article by, are you here, Rachel? Great work. Okay, she did some really nice work here. There's, and they looked at it on low, medium, and high settings, and they measured the clean air delivery rate. So 600 on low, or 800 on medium, and then maybe 900 or so. This is cubic feet per minute. And again, compared to the commercial units, which might be 200, this one's even 200, even under 200 cubic feet per minute. So they perform better. And then some of the figures on axes on the right talk about the sound level, which is shown in the triangles. So on low, the Corsi Rosenthal box is similar to one of the HEPA air cleaners. It is louder. And if you go to medium and high, it will be louder. So that's a drawback. But if you look at the cost of the units per cubic foot per minute that's moved through them, the Corsi Rosenthal box wins hands down. Those are shown in these circles here. Dollars per CADR. And you can see that the numbers are much, much lower for the CR box compared to the commercial units. And these have become a famous kind of do-it-yourself way of air cleaning, and they are really, truly very effective. They've been, school projects have done them. UC Davis has built them and distributed them. And CBS Evening News ran a segment on them where the host Nora O'Donnell built one together with the medical specialist correspondent John LaPook. There was an article in the Smithsonian magazine about this, the home air purifier that's been saving lives during the COVID-19 pandemic. And then one of them was even built by school children, I think in Connecticut, and delivered to the White House. And they called it Air Force One. Okay, so I want to wrap this up and say that, kind of what inspired me along the way is that engineering is the application of math and science to solve problems. That's what got me into this field, and I'm glad to have seen that our work has come to fruition. Well, I'm sad about the pandemic, but glad that we were able to help. And so to summarize, engineers have really played a critical role in pandemic response. And second, I've shown you here how we can apply an engineering framework to understand and predict the movement of viruses in the environment, and I mean the indoor built environment and the outdoor environment. And then thirdly, that there are engineering interventions such as ventilation and filtration and others that reduce the amount of virus in indoor air and thus reduce the risk of transmission. And so with that, I'd like to thank you for your attention, and I welcome questions now.
So thank you so much, Linsey. And I actually didn't know Linsey was going to like focus so much on the boxes. So thank you for that. We do have some questions that were provided with the RSVPs. So I'm going to ask one of those first, and then we'll go to the audience and we'll bounce back and forth with those. So the first question, Linsey, is what is your favorite virus?
I don't like that I have to just pick one. It's like picking among your children, like your favorite children. But I would have to say influenza virus, because that's what got me into this a long time ago. And then Ebola virus. We did some work on Ebola virus during the outbreak around 2014-15. And Ebola virus is really interesting to me because it's filamentous, and it has an envelope. So viruses come in two different types. They have an envelope, which is like a lipid bilayer, or they don't. And Ebola virus has an envelope. A lot of what we study does. And then it's also long and filamentous. And this made it a challenge because we weren't going to work with Ebola virus in our laboratory. We wanted to use some surrogate. And all of the other viruses that are filamentous and enveloped are like Marburg and other really nasty things. And so that presented a challenge to us. And I would love to figure out how to work with something like that that's not Ebola so we can better understand how it moves around.
Question from in-person audience.
Hey, Linsey, great talk. So we had SARS and then MERS and then coronavirus, COVID. Will there be another coronavirus, and is that the greatest public health threat? Or what should we be looking out for, especially in the context of now we have all these great tools to build vaccines and new technology that way. So will there be another outbreak like this in our lifetime?
Probably. I was a lot of people were expecting it to be influenza, and there's still the threat of a big influenza pandemic. That's always there. We got lucky in 2009. There's concerns right now about H5N1, avian flu that seems to show some transmission in mammals. I wouldn't be surprised if there's another coronavirus. If I had to put money on it, it'd be flu or coronavirus. I don't know which one. The fact that it was SARS-2 here, the coronavirus, was a little bit of a surprise because everyone's been worried about flu. But I think after seeing SARS, the original SARS in 2002-03, and now this one, and MERS, I think that's got to be a high priority too, along with flu. Given population growth, the stress we're placing on the environment, I'm going to bet that we will see another pandemic in our lifetimes, unfortunately.
Right. We're going to go to one of the RSVP questions for the next one.
Yeah, sure.
Linsey, as we look at decreasing transmission of COVID, and now we've got all these different Omicron variants, do you have an update on our understanding of relative to previous variants? How long Omicron variants live in the air, what their inactivation rate is, how long they survive on services, et cetera?
Yeah, that's a great question. When Omicron emerged and it was clearly more transmissible than previous variants, one question was, well, is it because it survives better, it persists better? And Paul Davish's group at the National NBAC, I can't remember exactly what that stands for, but it's one of the national labs that focuses on bioagents, has done the research and recently presented and showed that Omicron does not appear to survive any better. It's not like hardier, it's not more persistent than previous variants, but I think what's probably going on, what Don Milton's group has shown at the University of Maryland, is that people who are infected with Omicron release more virus in aerosol particles compared to the previous variants. So you have a stronger emission source, a higher emission rate, to put it in engineering terms, with Omicron that makes it more transmissible. There's also questions about kind of immune evasion and an infectious dose, but we know for sure that people with Omicron seem to emit more virus.
Thank you. Questions from in-person? Yep.
Thanks. I was curious about, so on your images and showing, this misconception of the free-floating virus all by itself and the statement about the physics being the same in terms of the particles. And have you thought about just like extracellular vesicles or sort of viral packages within aerosols and how that may be different from sort of the single virus by itself? And it's maybe as compared to aggregates? I'm just curious about your kind of thoughts.
Yeah, that's
on
a good
those.
question. We haven't thought about that because I just heard about that a few months ago when there was that paper that came out where they were talking about, was it temperature differences and like extracellular vesicles? I think the immune response was different. I think that's an interesting question to look at. Like, does that better protect viruses, perhaps? So yeah, we'll have to add that to the list. Thanks.
All right, Linsey, somebody saw a while back that ASHRAE, the American Society for Heating, Refrigerating, and Air Conditioning Engineers, is developing a standard for pathogen mitigation for indoor air. I'm not sure if you are involved as part of that. My question is, what's the typical timeline for ASHRAE standards to be implemented?
I'm not involved in that, and I have not been involved in ASHRAE standard making in the past, but I know from colleagues such as you that it can take years for ASHRAE standards to be developed and implemented. And those standards are important because those can be enforced through building codes. And so that's where kind of the rubber hits the road. I can't say I was on their infectious aerosols position document, and that took us 2 years just to come up with a list of positions. That wasn't even standards. So I'm glad they're doing this. We need to be patient.
You noted we need to expect another pandemic, and you also noted that on many fronts we didn't do a very good job both in communicating and being able to adapt to the new information as we got it in COVID. What do you think are the key lessons we've learned from COVID, both in terms of the public health aspects of like ventilation in schools and how we communicate that broadly so people will accept those as we go forward?
Okay, so I can speak from expertise on the first question about what do we learn for schools and things, and that is that we have not appreciated the importance of our indoor air on health and the role that it plays, not just for infectious disease, but just for overall health and both mental and physical health. And so there's a lot of room for growth there. If you think about our water quality, we have drinking water standards, we have water treatment everywhere. We haven't really done anything about the indoor air that we're breathing all the time. And so that's one important lesson. In terms of the kind of public health and communication, there I speak from experience, but not, I'm not an expert in that. But I can say that, yeah, it was a mess. It was a disaster. I worry about misinformation. And I think what agencies and communicators can do better is to be, I don't know, I worry about how the public would take this, but to be more transparent about the uncertainties, the difficulty of making decisions, where you're making hard trade-offs, and acknowledging that you are making those trade-offs, like, okay, well, it's, there's economic considerations, there's social considerations, there's physical health considerations. We're deciding to do this because we can't have everyone stay home forever. Obviously, that didn't work in China, and to be more transparent about that and acknowledge those trade-offs rather than, unfortunately, what I saw was twisting the science to try to fit the desired policy, which was prioritizing other things.
All right, so we're going to have one more from the RSVP questions and then one more from the audience that's here. Linsey, do handheld portable HEPA air purifiers create a bubble of safer air to aid in preventing COVID?
Yeah, I think they're asking about like a small HEPA air cleaner. So I talked about the ones that you might have in your home that are kind of this size, like a size of a humidifier or dehumidifier. You can also buy much smaller ones that are battery powered, and you can just take to the restaurant and put on your table. And I would say, if it's powerful enough, has a high enough clean air delivery rate, you would create kind of a zone of cleaner air. It's going to depend on the airflow in that space also. It can't hurt, it could help. So yeah, I would say it could only help.
And one more from the audience.
Hi, that was great. So I'm a public health worker, not an engineer, so I've been kind of trying to learn a lot more about it because I've been working in schools. And one thing that we find challenging is, a lot of schools can't afford HVAC, so we try to, get them to the Corsi Rosenthal box or other filters. But then we've been trying to place sensors in different parts of the room to see where the most effective filter is. I'm just curious, kind of your perspective on that, because it's also, there's the practical field challenges of getting teachers to plug them in.
To turn them on and off.
Yeah, and then also to place them in ways that don't, get into the way. So we've been trying to do education stuff, but then it's also just the engineering of the air mechanics within the room, where the air exchange doesn't seem to be uniform. And again, not an engineer, but that's what we're noticing.
Yeah, it's not. Yeah. There's so much variability in the room, so I can't give one answer, except that, in this case, if you're concerned more about the teacher and if the teacher's talking more, I think having it closer to the teacher is probably more useful. But there's also considerations of the cord. You don't want people tripping over it.
Right.
So there's other considerations. And then who's turning? Teachers have enough to do.
Yes,
I
yeah.
admire anyone who is a teacher, and to ask them to worry about managing this extra thing, it's too much. And so I think we need to have ones that are programmed to go on and off. Maybe they have a sensor or just on a timer. Because I told my kids going to school, I told them, because they put them in the schools, I was like, make sure that it's turned on. I'm telling you, your job is to turn it on every morning, because they weren't turning them on. And I understand that. They've got a zillion other things to do.
So educating the communities might.
Educating the communities and providing cleaners, I think, with a just timer, goes on at 8 o'clock, off at 3 o'clock. It seems like a pretty simple thing to do.
Right. Cool. Just curious.
Yeah.
All right. So great talk, Linsey. Thank you so much one more time. And
Thank you.
I can't think of a more contemporary issue, sort of in the moment, is hearing somebody talk about what we know about COVID-19 and how it's transmitted. And Linsey really is amongst the few people in the world who's truly an expert on airborne viruses. And so we're very fortunate to have had her here today. As a token of our gratitude, I'm excited to present you with a gift of UC Davis tchotchkes. I actually have, so that's pretty heavy. There must be something good in here. So this is for you.
Oh, wow. Thanks.
And let's all give Linsey one more wonderful round of applause.
Thank you so much.
But don't leave yet. Don't leave yet. So mark your calendars, everybody. April 19th, we're going to have our next Dean's Distinguished Speaker event, which will feature Kim Budil, Director of Lawrence Livermore National Laboratory. Kim is a double alumna of the UC Davis College of Engineering. And so hopefully you'll be back on April 19th. So please join us now for a reception in this space until 5:45 or so. So for the next 45 minutes, Linsey will be here. You're all here. We can mingle, have a good time, and talk to each other. And once again, we appreciate your attendance today, and we hope to see you again on our next Dean's Distinguished Speaker event on April 19th. Thank you so much.